So later on in the course, we're going to study the geometry of Lipschitz images of Euclidean space. So for example, here I have a Lipschitz function that goes from Rm into some Euclidean space Rn. And one of the results that we're going to show is that at almost every point in the image of a Lipschitz function, there is a tangent plane, in the sense that as I zoom in at almost every point, at this point in the image begins to look more and more like a m-dimensional plane. Okay, so one way that you might try and prove this is saying, well, at almost every point in the domain, my Lipschitz function is differentiable, which means that on small scales around x, my function looks approximately like a affine map. And so that means that I can just take this plane to be the image of Euclidean space under this affine map. Now, the problem is that a Lipschitz function is not always, so at almost every point, the function is differentiable, but that the linear approximation, or the derivative of the linear approximation, may not always have full rank. And so there may be some points where the affine map is collapsing space into a smaller dimensional space. So for example, that could happen if, let's say, along an interval here, all these points got mapped to the same point. So in this case, the derivatives all along here are 0-dimensional. And so that means I can't use the derivatives along this interval to get information about the geometry at this point. Now, what Sard's theorem says is that as far as the image is concerned, the set of points where the derivative has small rank is negligible. So Sard's theorem says that if we have a Lipschitz map from Rm into some Euclidean space, then the image of the set of points where the rank of the derivative is strictly less than m has Hausdorff m-dimensional measure 0. So let's sketch the ideas behind the proof of this theorem. So first of all, I'm going to assume without loss of generality that the Lipschitz constant is at most 1. And then I'm going to define a set E, that is the set of all x inside the unit ball, for which the derivative exists and has rank strictly less than m. So my goal is to show that the image of this set has Hausdorff m measure 0. If I can show that for the unit ball, I can show it for any ball. And then that will imply that the image of all points where the derivative has rank less than m has Hausdorff m measure 0. So notice that by definition, every point inside the set E is a point of differentiability, which means I can find arbitrarily small balls centered at points in E where my function f is approximately the linear approximation function at the point x, where recall that the linear approximation of f at x is equal to f at x plus the derivative of f at x times y minus x. This is the linear approximation. Okay, so because I can find arbitrarily small balls at each such point, that means that by Vitali, this implies that there exists a collection of disjoint balls, so bj equal to bxj rj, disjoint, so that the xj's are in E. The rj's are small enough, but in particular I want them less than 1, so that the Hausdorff measure of E is exhausted by the union of these balls, and also that f is approximately its affine approximation at the center of the ball in Bj. So in other words, what this means is that the difference between f and its linear approximation divided by the radius of the ball is less than epsilon inside the ball Bj, for some epsilon that I'm going to set to 0 later. So let's take a look at what's happening inside the ball Bj. So let's say here's the ball Bj. Now under the function LFXJ, recall that xj is a point from E, which means that the derivative at xj, it has rank less than m, which means that this affine map is going to take this m-dimensional ball to a subset of a m-1 dimensional space. All right, so this is LXJ of Bj. And moreover, because we're assuming that the Lipschitz constant of f is at most 1, that implies that the diameter of this set is at most the diameter of BJ. Okay. Now, furthermore, because f is approximately the linear approximation in here, that means that the image of BJ under f is inside a small epsilon neighborhood around the image of this set. So this is saying that the image of the m-dimensional ball BJ under f is concentrated around is in the neighborhood, a small neighborhood of a m-1 dimensional set, or a subset of an m-1 dimensional plane. And so then what that tells me, actually, so one can show that the Hausdorff content of the image of BJ, because the image of BJ is concentrated around a m-1 dimensional plane, that implies that the Hausdorff content is at most epsilon times the Hausdorff content of BJ, where epsilon is how close f was to its affine approximation. Okay, so with this in hand, then we can show that the Hausdorff content of f of E. So recall that if I show that this is 0, then that implies Hausdorff measure of f of E is 0. This is at most the sum of the Hausdorff contents of f of the individual balls, which are at most some constant times epsilon. Now recall that Hausdorff M content in Rm is equivalent to Lebesgue measure. So this is actually comparable to the sum epsilon times the sum of the Lebesgue measures of these balls Bj. And because I picked the radii of the balls to be less than 1 and the centers are inside the unit ball, that means that this is a union of disjoint balls inside the ball center at 0 of radius 3. So this is at most epsilon times the Lebesgue measure of the ball center at 0 of radius 3. So now I have that the Hausdorff content of f of E is at most epsilon times some fixed number for any epsilon. And now I let epsilon go to 0, and that completes the proof.